Unbalanced phase loads in a three-phase motor can stem from several potential causes. Firstly, an unbalanced load is a common culprit. This occurs when one or more phases is carrying a significantly different load than the others. Several factors can contribute to an unbalanced load, including faulty motor windings, mismatched loads connected to the motor, and mechanical issues in the driven equipment. Secondly, loose or faulty connections can also lead to current imbalances. Poor connections can increase resistance in one or more phases, resulting in lower current flow through those phases. Thirdly, damage to the motor itself can cause uneven current distribution. Internal damage, such as shorted windings, can disrupt the normal current balance. Fourthly, overloading the motor can also contribute to current imbalances. If the motor is running at or near its rated capacity, it may experience increased current draw, which can exacerbate any existing imbalances. Fifthly, voltage imbalances, even if slight, can affect current flow in different phases. Although the supply voltage may appear stable, even small imbalances can lead to noticeable current differences. To effectively troubleshoot unbalanced phase loads, several steps can be taken. The first step is to check for loose or faulty connections. Carefully inspect all electrical connections to ensure they are tight and secure. Pay attention to any signs of corrosion or damage that could indicate a poor connection. The second step is to measure the voltage across each phase. Using a voltmeter, measure the voltage between each phase and the neutral point. The reading should be within 1 to 2% of each other. Significant voltage differences can indicate a problem with the power supply or distribution system. The third step involves testing the motor windings for continuity and resistance. Use a multimeter to measure the continuity and resistance of each winding. The windings should have similar resistance values. Significant differences in resistance can indicate damaged or shorted windings. Fourth step is to monitor the motor's current draw over time. If the current imbalance persists, monitor the motor's current draw over time using an ammeter or clamp meter. If the imbalance worsens, it could indicate a developing fault in the motor. The fifth step is to inspect the driven equipment. If the motor is connected to any mechanical equipment, inspect it for any binding or excessive friction that could cause uneven load distribution. Mechanical issues can put additional stress on the motor and lead to current imbalances. To elaborate further, let's delve deeper into each of these potential causes and troubleshooting steps. When examining the possibility of faulty motor windings, consider that internal shorts or open circuits within the windings can significantly alter the current flow in each phase. A short circuit provides a low resistance path, causing excessive current draw in that phase, while an open circuit can reduce or completely stop current flow. To test for this, a multimeter set to measure resistance is essential. Disconnect the motor from the power supply and measure the resistance between each pair of windings. For example, if you label the motor terminals as tone T2 and T3, you would measure the resistance between tone and T2, T2 and T3, and tone and T3. These resistance values should be very close to each other. Significant differences, such as one reading being much lower or higher than the others, indicate a winding fault. Also, check for continuity between each winding and the motor frame. There should be no continuity, indicating no short to ground. If there is continuity, it suggests insulation breakdown, which is a serious issue requiring motor repair or replacement. Mismatched loads connected to the motor can also create an unbalanced load. This often occurs in applications where the motor drives multiple devices or pieces of equipment, and one or more of these devices requires significantly more power than the others. For instance, if the motor is driving a conveyor belt and the pump requires significantly more torque or horsepower, the phase supplying power to that load will experience a higher current draw. To address this, analyze the power requirements of each device connected to the motor. Ensure that the load distribution is as balanced as possible. If one device consistently draws significantly more power, consider redistributing the load or using separate motors for each device. Mechanical issues in the driven equipment can also contribute to unbalanced loads. Binding or excessive friction in bearings, gears, or other mechanical components can increase the load on the motor, causing it to draw more current. This increased current draw may not be evenly distributed across the phases, leading to imbalances. Regularly inspect the driven equipment for signs of wear, damage, or misalignment. Lubricate moving parts as needed and address any mechanical issues promptly to prevent them from affecting the motor's performance. Loose or faulty connections are a frequent cause of electrical problems, including unbalanced phase loads. Connections that are not properly tightened or have become corroded can create increased resistance, which reduces current flow in the affected phase. Over time, this can lead to overheating, voltage drops, and ultimately, motor failure. When inspecting connections, pay close attention to the tightness of screws and bolts. Use a torque wrench to ensure that connections are tightened to the manufacturer's specifications. Look for signs of corrosion or oxidation on conductors and connectors. Clean corroded connections with a wire brush or chemical cleaner and replace damaged connectors. Also, check for any signs of overheating, such as discoloration or melting of insulation. These signs indicate a high resistance connection that needs immediate attention. Voltage imbalances, as mentioned earlier, can significantly impact current flow in different phases. Even small voltage differences can lead to large current imbalances, especially in motors. Voltage imbalances can arise from various sources, including unbalanced utility power, uneven distribution of single-phase loads on the same circuit, or voltage drops due to long cable runs. Measure the voltage between each phase at the motor terminals using a voltmeter. Calculate the percentage of voltage unbalance using the following formula. Voltage unbalance percentage equals the maximum deviation from the average voltage divided by the average voltage multiplied by 100. A voltage imbalance of more than 2% can significantly reduce motor efficiency and lifespan. If voltage imbalance is detected, work with the utility company or electrical contractor to identify and correct the source of the imbalance. Testing the motor windings for continuity and resistance is a crucial step in diagnosing internal motor problems. A multimeter is the primary tool for this task. Disconnect the motor from the power supply and discharge any capacitors that may be present. Set the multimeter to measure resistance in ohms. Measure the resistance between each pair of windings as described earlier. The resistance values should be consistent and within the manufacturer's specifications. Also, check for continuity between each winding and the motor frame. There should be no continuity, indicating no short to ground. If there is continuity, it indicates insulation breakdown, which is a serious issue requiring motor repair or replacement. Monitoring the motor's current draw over time can provide valuable insights into its performance and identify potential problems early on. Use an ammeter or clamp meter to measure the current in each phase while the motor is running under normal operating conditions. Record the current readings and track them over time. Significant changes in current draw, especially increases or imbalances, can indicate developing problems such as winding faults, bearing issues, or overloading. Implement a regular monitoring schedule to detect these changes early and take corrective action before they lead to motor failure. Inspecting the driven equipment is essential for identifying mechanical issues that could be affecting the motor's performance. Look for signs of binding, excessive friction, or misalignment in bearings, gears, belts, and other mechanical components. Rotate the driven equipment by hand to feel for any resistance or unusual noises. Check the alignment of belts and pullers to ensure they are properly aligned. Lubricate moving parts as needed and address any mechanical issues promptly to prevent them from putting additional stress on the motor. Now, considering the initial readings provided, the reported phase currents are 72 amps, 69 amps, and 60 amps, which indicate a noticeable imbalance. Given that the motor's rated full load amperage, or FLA, is 74 amps, the A and B phases are operating near full load, while the C phase is significantly lower. This discrepancy suggests an issue affecting the C phase. Based on the troubleshooting steps, it's advisable to start with the simplest checks first. Begin by inspecting all electrical connections to ensure they are tight and secure, particularly those associated with the C phase. Next, measure the voltage across each phase at the motor terminals to rule out voltage imbalances. If the voltage readings are within an acceptable range, proceed to test the motor windings for continuity and resistance. Pay close attention to the resistance of the C-phase winding, as a significant difference compared to the other windings could indicate a fault. If the motor windings appear to be in good condition, inspect the driven equipment connected to the motor. Look for any signs of binding or excessive friction that could be causing the C-phase to draw less current. If the cause is identified as an unbalanced load or voltage imbalance, take steps to correct the issue. This may involve redistributing the load, correcting voltage imbalances in the power supply, or upgrading the motor's wiring. If the motor shows signs of damage or internal faults, it may need to be repaired or replaced. Consult with a qualified motor repair shop to assess the extent of the damage and determine the best course of action. Regularly monitor the motor's current draw to detect any changes that may indicate developing problems. Implement a regular monitoring schedule to track the current in each phase and identify any significant changes or imbalances. Consider using a phase monitoring relay to protect the motor from damage due to prolonged current imbalances. A phase monitoring relay can detect voltage or current imbalances and automatically shut down the motor to prevent damage. In summary, troubleshooting unbalanced phase loads in a three-phase motor requires a systematic approach. By following the troubleshooting steps outlined above and addressing any identified issues promptly, you can ensure the motor operates efficiently and reliably and prevent costly downtime and repairs. Always prioritize safety when working with electrical equipment. Disconnect the power supply before performing any inspections or repairs, and use appropriate personal protective equipment such as insulated gloves and safety glasses. If you are not comfortable working with electrical equipment, consult with a qualified electrician. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or motor repair shop for specific diagnosis and repair recommendations. Remember that motor failures can be costly and disruptive, so it's essential to take a proactive approach to motor maintenance and troubleshooting. Regularly inspect and maintain your motors to prevent problems before they occur. By following these guidelines, you can ensure your motors operate efficiently and reliably for years to come.